As robotic technologies continues to evolve, robots capable of interacting safely and effectively with humans are essential. In this video, we will present an introduction defining key terms, a new quasi-direct drive actuator design, the Pulse 11560, a new set of experimental procedures for better actuator comparison, a full specification including backdrive torque and bandwidth of the Pulse 11560, and finally, a conclusion section where all results will be discussed. The design of actuators is crucial for achieving effective physical human-robot interaction, since providing precise and controlled motion is key. To achieve enhanced and safe dynamic performance, actuator design must focus on three main areas. Proprioception, the ability to perceive one's own body position and movement, plays a crucial role in human motor control and coordination. By integrating proprioceptive feedback mechanisms into highly dynamic actuators, it is possible to facilitate real-time adaptation and collaboration between human and robots. Responsive actuators adapt to various scenarios, facilitating smooth interactions in unknown environments. Responsiveness is a characteristic that can be represented by actuator bandwidth. Actuator transparency defines how easily the system can be driven from the output side. Backdrivability provides a good measure to quantify this characteristic. The work presented in this contribution aims to introduce the design of the Pulse 11560 actuator, as well as to define a set of methodologies to correctly characterize actuator performance, setting up a starting point for future research. Bandwidth can be broken down into three different types, each providing unique information. Current bandwidth reflects the capabilities of the control, inverter, and electric motor to adapt to a required current demand. Speed bandwidth indicates how quickly the actuator, including mechanical system, adapts to a change in speed and rotational direction. And finally, torque bandwidth represents the capability of the actuator, again including mechanical system, to respond to changes in torque demands. It's important to remark that current bandwidth is not equivalent to torque bandwidth, since all the mechanical effects are neglected. A direct or a quasi-direct drive approach implies designing actuators with low gear ratio or without transmission. This type of actuator provides high bandwidth and backdrivability at the expense of maximum output torque. On the other hand, actuators with high gear ratio transmissions provide a greater torque-to-wear ratio and display a reduced mechanical backlash at the expense of dynamic performance, namely impact absorption, acceleration, bandwidth, proprioceptive capability, and friction, among others. The Pulse 11560 actuator design was performed from the ground up to provide outstanding dynamic response and proprioception capabilities. In order to achieve this, a new electric motor, P100, was developed with the objective of maximizing torque per watt and kilogram while operating at low speed and high torque. A new 5-to-1 transmission was tailor-made with the aim of reducing rotational inertia and backlash for the specified operational envelope. In order to allow for good proprioceptiveness, a novel high-stiffness torque sensor has been also developed and integrated within the actuator to provide an accurate measurement of both internal and external torques. The stimulus for a robust characterization of bandwidth in geared actuators must include changes in direction of movement, for example, a sinusoidal signal, which better represents real conditions for robotic applications. Calculating the bandwidth of an actuator with a step response experiment isn't reliable due to the inherent nonlinear effect of backlash, among others, which significantly influences the achievable bandwidth during reversing torque operation. We propose a new methodology to accurately derive backdrivability. Low backdrive torque actuators are essential for developing human-centered robotic devices. Experimental procedure consisted in measuring the angle at the input and at the output of the actuator. Then, the ratio between the respective angular velocities was calculated. Since the actuator is not backlash-free, the backdrive torque is defined as the torque at which the ratio between the velocities recorded by the input and output encoders converges within ±1% error of the design value, 5-to-1. All the experiments started finding optimal Kp and Ki according to methodology found in bibliography. However, since the method is known not to be 100% accurate, constants are swept below and over a cautiously defined threshold to ensure that the combination of constants that achieves the maximal bandwidth performance are selected. The actuator bandwidth corresponds to either the frequency at which the response is attenuated below -3 dB, or the frequency at which the phase shift exceeds -180 degrees, whichever is reached earlier. This process led our team to accomplish a design capable of providing 62.5 Nm at 36 RPM with a mass of 1.25 kilograms. Backdrive torque measured according to the previously mentioned method resulted in 0.37 Nm. And finally, actuator bandwidth displays for each of the 3 different experimental procedures showed superior performance compared to examples in state-of-the-art literature. Therefore, the Pulse 11560 actuator was developed from scratch according to the Quasi-Direct Drive Actuator design philosophy, where all the systems come together to achieve outstanding dynamic performance, proprioceptiveness, and transparency. In addition, a new set of experiments was proposed and described to accurately characterize and compare actuation systems designed for modern robotics. This procedure has demonstrated how the Pulse 11560 performs according to the claimed specification. We invite you to read this contribution in order to get a more detailed overview on our design, experimental method, and setup. As we navigate the complexities of physical human-robot interaction, it becomes evident that significant strides are yet to be made.